So this is a video of a technical review of my CNC hybrid controller. I've certainly done videos of the machine operating before, a plethora of those, and I've also shown the sensors and some of the spindle control stuff in action. But I've yet to go inside the box and really explain in depth why I chose some components and why I wired things the way they did, some of my methods for doing it. And I just wanted to go into a technical review for the CNC controller and explain and hopefully answer some of the questions that I've received on a regular basis. In addition, I offer these plans, actually sell them as a package with the PDF of the mechanical and electrical schematics, as well as a parts listing, BOM, and an Excel spreadsheet with all the parts that you need. It's a turnkey package. This CNC controller at the time, with trial and error, was probably around $1,000. So it's certainly not a simple controller, but hopefully by putting this package together, it simplifies it and gets you running the first time. And hopefully this video helps explain and answer some of the questions that people have had. So let's get going. Okay, so let's start with the inside of the box. Best place to start. To start off, this is a NEMA 412 Wagman box. So I have actually the part number in my listing. Pretty deep box, pretty big box, and a heavy-duty box. Something I probably wish I hadn't mounted on the machine by myself initially. Very stout. Comes with a white folded backplate. I don't know if you can see it underneath. That's just a steel backplate that I drilled and tapped for all the holes. Everything is DIN rail mount except for the Gecko drivers, which are on a custom aluminum heatsink that I made up. All the components are, actually I shouldn't say all of them, the transformer and the PMDX are also threaded and tapped onto the backplate. The transformer is so heavy I actually through bolted it because I was worried about thread engagement. Probably, I think it's like 20 pounds for that Tolroyd transformer in that power supply package. Also, you'll notice is I have a muffin fan. I believe this is a 4 or 5 inch Rittal muffin fan, which has a filter on the intake, and then I also have a filter up top for the output, which just naturally pushes in fresh air and forces that warmer air, if we'll call it that, out. I was worried about that. These heat sink, it works really well, but it also still leaves these guys pretty warm. So it's nice to have a fresh air supply in here to keep those guys as healthy as possible. Okay, so I'll just start at the bottom of the panel, and actually I'll just grab a better picture here, and then we'll come back to this door harness stuff and what I've got going on with that. At the bottom of this DIN rail, you'll see on my immediate left here, I've got a Carlo Gavazzi solid-state relay. This guy I'm using to switch on and off the router. And how I'm doing that, and I'll come back down here with the control stuff, is I'm using the PMDX 122 breakout board in conjunction with this router. It's got its own onboard, I forget what the rating is, but it has an onboard cube relay on there. But it's not user replaceable. It's also probably not nearly as high quality as this solid state relay. This guy's very easy to change should I ever burn it out. I don't think I ever will. But this takes the heavier load because that onboard relay can't handle the type of motor load that I've got, inductive motor load that I've got. Or probably just a better way I thought to do it. So this guy, I'm taking that relay, and that relay contact is switching this relay coil, and then the load of the actual router, or the line of the load, is actually coming off of here. And then it's just picking up a neutral and a ground off my my line bus, which I'll explain right now. So my main wires coming into the panel for power land on this AC bus, and this consists of line, neutral, and ground. This is 120 nominal AC, single phase AC. Here I have some AC fuse terminals. These are just flip-top Phoenix Contact 5x20 millimeter fuses for basic protection. I've also got an in-panel circuit breaker, kind of like my water controller. It's really just for isolation and turning off the panel in one shot without having to go back to the panel and flip it or unplug the machine, the main power cable. It's also got its own breaker for that spindle, which coincides with this relay. This has a pair of auxiliary contacts so that if this breaker ever trips, or if I switch it off, or for any reason, this will go back to the PMDX, and my computer will know to be in a fault or an e-stop. Otherwise, this is just a dumb breaker, and if that router overloads and that breaker trips for any reason, nothing really knows about it other than me knowing that the router stopped, which is not a really good. It's not good to rely on humans inherently, because we get distracted or just forget. So it's not like perfect. The router is not totally monitored, but that gives me basic protection that I was looking for. And then scooting over here, this is the main AC contactor for the entire panel. I'll explain it down when I go back up to the door harness. But basically, this turns power on to the entire panel, front end of the breaker, and this takes the load. This is actuated, the coil, with a momentary push button switch. And then also it's a double push button switch, which you'll see in another picture, green and red. Next to that, I have my e-stop inputs. There are 2 machine-mounted e-stop buttons and 1 on the panel on the front of the door. So there are 3 emergency stops total, and those kill power to the contactor, which basically shut off the entire machine. The only thing they don't do is they leave the PC on, and you just go to an e-stop mode. So I'm basically turning off your line power to the panel and killing everything, respectively. And I'm also running an e-stop fault to the PMDX 122 so that the computer knows to go to e-stop and stop spinning code out, and knows to stop wherever, it's not perfect. You really don't want to stop a program in an e-stop and expect to have accuracy, but you certainly will save yourself from injury or damaging something or breaking a tool, potentially. That's the thought anyways. These 2-tier terminals here are for my motor connections. They're phase A and phase B of the DC stepper motor. And then I've got also this middle terminal here is for the shield. I did use shielded motor cable, and I carried my shields over and properly bonded them to ground so that I shouldn't have any noise issues. Scooting over here, my proximity sensor inputs. I've got 4 here, as well as my touch plate is my last input that I'm using here. Let me just grab another picture here, and I'll show you where we're going up to the next in-rail. So up here is a better picture of the 4 or 5 really Gecko 203V stepper motor drives. Beautiful drives. They've worked continuously and hard for a long time. I love these drives. Gecko drive has probably the best support out of all the components in this panel. You can call the owners up and talk to them and give them really heavy technical questions, although probably not even my questions haven't even been that heavy, but they're very knowledgeable. It's not like you're calling some dumb customer service or technical support. You're talking to the guys that designed that PCB when you call them. So really good shout out to this company. They make a really good quality product where you really don't have to call them that often, but when I have, they're excellent. Basic wire connections here. You've got your DC input. I think this transformer outputs an unregulated about 56 volts DC. And then over here, your phase A and your phase B motor connections. I know this is unusual because I'm using a ground conductor in this multi-core cable. I just didn't feel like buying a 5 or 6 core, whatever the next nominal was, just so I can follow my schematic carefully enough where I don't need an extra black numbered conductor. This is my step and direction signals in common, which go up to the PMDX board, which I'll get up to next. Those go directly over there. And then this is my current set resistor for the motor drive size correctly. And that resistor is just very crudely just screwed into the screw terminal. This 5th guy here is just a spare in case I really, if I burn out the drive or if I do something wrong, where I could just take all these leads, unscrew them, and put it over here and be up and running in 2 minutes without having to send this back to California, wherever they are, and debug it and then be down. I thought it would be better to put it here than in a box because it's just there's no better place than to have it ready to go in the panel. Underneath it, you'll see that these are screwed and tapped onto a very stout aluminum heatsink. It's a finned heatsink, and then there's this aluminum post that I made, just kind of like spacers that are tapped from the bottom and the top. And then I notched this out and fit them in there. Also underneath, these are drilled and tapped. They're 2, I think they're 4-inch muffin fans or 3-inch muffin fans that keep this finned heatsink pretty darn cool in addition to the main enclosure heatsink. So the next in-rail up is my main rotary disconnect. I would have liked to have put this on the AC bus area. but it just kind of worked out where you work out with mechanical space. That just worked out to be the best place. I think I ended up putting end stops on the end of this to hold it in place. It was just that I didn't. I had to mount it in the panel first to perfectly center the location. Next to the right of it is my fused DC bus. This comes off the power. Like I said, it's unregulated 56 is what it works out to be DC output. I basically took these leads, I snipped them, I put ferrules on them, proper wire connections, and because they weren't long enough, and the fact that this thing lacks screw terminals, I really do think that these should have screw terminals just like this does. I don't know why they don't actually put it in there. So what I did was I squeezed two feed-through terminals in there. I put a small little DIN rail and put it in place there and kind of made my own. I carried those extra wires in the wire duct and then over to my DC bus. Same. I don't use the other outputs. I just use those. I think they come over. Yeah, they come over here. I do take the. Sorry, excuse me. I take the 12 volt output as well, and that comes over to my 12 volt DC bus for the actual inductive proximity sensors, which you can see these slim interface relays of what those are for. So these are all fuse terminals. There's actual glass 5 by 20 millimeter fuses in them. They just flip up to change them. Then I come over to here to my 12 volt DC bus, and that's what this fuse is for. So the 12 volt DC is for this proximity sensors and these interface relays, and the 56 or 54 volt DC bus is just for the stepper motors themselves, the drivers. And these are, I believe, they're slim interface relays. They have an LED indication when they're high, and I'm using one set of their contacts to keep them basically on all the time. They're powered in a way that they're fail-safe, so that I have to be sensing the wires have to be basically uncut. So if a wire breaks, the machine will go straight to e-stop. It'll fault as though it hit an end of an axis or hit its target, should I say. So that the machine can never operate without proximity sensors. I know that would be kind of a pain and unusual for the thing to have a wire break, but you sure as hell don't want to find out that the wire's broken or something's wrong when you hit the end of your axis and you slam into it. You really do want to just stop the machine because one of your your safety or your proximity sensors isn't working. So that's the logic for that, and I'll get into that when I go show you the schematics. And up at the top, I know it's hard to see, we've got our PMDX 122 with the parallel ribbon cord, which comes down, and I'll show you in another picture. I have all these terminations at the bottom of the panel. We've got our basic sensor I/O. As I said, I'm taking this cube relay for the spindle, and I'm taking that down to flip a larger solid-state relay down on the lower DIN rail. I've also got my 4 primary X, Y, Z connections here. Basically, I've got twin ferrules for the 2Y motors, because there's 2Y motors on this machine on either side of the gantry. So I twin ferrule them together into the same input rather than slaving one. And what that does for me is that keeps not only this being an extra, but this could be potentially a 4th axis if I would like it to. And that's why this guy is free up here. I could actually add a 4th axis, which is more desirable. You can actually put the 2 Ys and then slave them together in software mode, in Mach 3 or whatever control software you use. But this keeps me saving it because the PMDX only has 4 stepper motor outputs. So that's the interior of the panel. I'm going to try to explain a little bit more here and show you what's going on with the terminations at the panel. I'm going to pop up on a picture. I think this one's of me actually wiring the panel on my machine. I know it's a little bit hard to see, but you can see that all the terminations come out the bottom through what's called a split cable gland. It's actually made by Roxtec, where you just take these split cables and you don't have to actually cut any cables, even a parallel cable. They just come through and you put these little split glands in. I think they're much better for this application with not having to cut some of them, especially the parallel cable, and do a termination for that and come in the panel. I basically ran all the cables for the machine. I ran them through the cable carriers, ran them long, and snipped them to their respective lengths, and then terminated them everything while this thing was mounted on the machine. It worked out really nice, even though I had to sit on the floor for a while. So that is the inside of the panel and how it works. Let me just show you before I go to the schematics and the BOM and show you some of the other technical stuff. The wire harness. The wire harness comes up through one of the wire ducts and up to the top of the door on this flexible sleeving, which is really nice. It keeps everything organized. You don't have any wires hanging over the place, except for in this picture, this is just a ground conductor I was using as a jumper when I was testing it. This guy comes up to the door. You'll see right here I've got a donut on here, and that is just for sensing current. I just split that with a little connector so I didn't have to run a cable up and back and make that extra work. This senses frequency, voltage, and current, and displays in amps and watts, I believe. This is the other side of the disconnect handle, which connects in there when the door is closed, as well as my emergency stop. And you'll see my dual contacts. One is for is actual an input for the machine, and the other one is for the contactor to flip the contactor should I hit the e-stop, and also my on and off switch. So that's the wire harness for the door and how this thing's wired in, and that pretty much covers the inside of the panel. So I think what I'll do is I'll show you some of the parts of the machine. These are the two emergency stops that I've mounted on the machine. Again, all this cable on here is IGUS continuous flex cable. The motor cable is shielded. The rest is not. And these guys are all drilled and tapped with little cable mounts, so these are permanently fixed on the machine. Well, not permanent, but they're very well fixed onto the machine. These e-stops are placed in a location where I can easily reach either side of the machine, regardless of where I'm hung up. I don't really work on the sides of the machine. That is my primary work area in the front. There's also an e-stop on the front of the panel, which I'll show you, and I'll show you the front end of that. There's the panel meter, just displaying current. That's actually 1.23 amps. The machine normally runs, unless I'm pushing it, around 4 or 5 amps for the entire machine, not including the computer, but including the spindle, which is not bad considering the loads. You'd think it would be much more. This is the disconnect handle that you saw from the inside, the other portion of it. This is the on and off switch, which is also illuminated, which is a nice indication, and this is the e-stop with a little plate. And that's pretty much it. I've got this entire enclosure threaded and tapped into the steel structure of this machine, so it's really strong. And I actually had to make a bracket here because there just wasn't any place to tap it on this side of the machine, and I didn't want to cantilever it all. All the cables on the machine are wired back through IGUS cable carriers, which kind of match with the continuous flex cables that I never really have a failure. I used basic Home Depot security wire for a long time, stranded wire, and didn't have any problems, but I certainly feel comfortable with this machine running hours and hours on end, considering this is basically robotic cable. It's not very expensive. It's a great investment, and I definitely recommend anybody that's looking to get cable to go to IGUS. Another great company, I'll give them a shout out. Extremely liberal on samples, and they're very good with technical help. One note is with the stepper motors, the way these are wired, and I've mentioned this in my other videos, is that these have free leads off of them. They actually have 8 leads and they wire them in parallel. And you take them down to 4 leads. And one of the messy things I've found about these is you don't really want flying leads hanging off your machine. So what I did was I took those leads, staggered them, I cut them in staggered points, and actually soldered them to the continuous flex cable. Then I wrapped it in heat shrink over a harness, and I used the harness material, and it came out to be a really nice solution for cleaning up those wires and continuing into one solid cable and back into the wire duct, into the cable carrier. And this is actually wire duct right here. And it worked out to be a much better solution than just leaving the free leads and using, say, XLR connectors, which I used for a long time, but realized that I didn't need any kind of quick disconnect or any kind of thing. These motors just don't get changed out, and you just don't do anything with the wires. So adding an extra connection at the motor and then perhaps at the enclosure, a lot of people, and I certainly did for a long time, put XLR connectors or any motor connector at the panel. There's really no need for that. You should really terminate at a field terminal strip inside the panel. There should be almost no wire connections. The only reason I have a wire connection here is so that I can make it to a nice cable, and that should be the only wire connection from here to the panel. It minimizes potential for failure, keeps any potential for having bad connections, and that's kind of where I've shifted from when I originally started, just with experience and learning more about the machine. All right, so that's enough about the panel. I'm going to show you what I've got going with these plans here. This is a PDF plan. I've done these in AutoCAD. Basically, I've got mechanical views showing the exterior, interior, and a side profile view. I've explained this already, so I won't go too much into detail, but showing your terminals and some of your components, your PMDX up here, your power supply with the transformer and the disconnect, all that kind of good stuff. This is going to give you a nice overview of how to lay out the panel with some nice wire duct and cable management. And then I also go into detail here showing a field terminal strip, the upper buses and whatnot, and then also how I've got the transformer should you go with this transformer, which I think a lot of people do because it's affordable and it's a good product. And then I get into the schematics. Schematics are extremely detailed. They're point by point, so you just basically land wires and tag the wires associated. You don't have to. I do it because it's the right way to do it, and for clarity's sake, it's just a much better way to go because you can debug things a lot easier later. But I've assigned wire numbers for everything already. They're all unique, so unless they're common to each other. Layout from the power into the disconnect and contactor, push button switches, your e-stop and your field mount e-stops, your DC bus off of your transformer, your 3 cooling fans, panel meter, your circuit breaker, and your solid state relay on how to wire your spindle in. My spindle on my machine is hardwired, so I actually turn it on with the G-code. Your PMDX wiring, as well as your stepper motors. Your stepper motors drivers wiring right from the motor, how you wire it in parallel, in bipolar parallel, all the way back to the stepper motor driver, the Gecko drives, and continued. And then I show you how to wire in the inductive proximity sensors, regardless of which type you use. Pretty basic setup with the relay, interface relay, as well as a touch plate. And here, this could change depending on what type of machine you have. It's all very universal. So those are the plans I offer. I sell with those. I put a lot of time into it. I design them. I put a lot of thought into them. They work. I've been using them for a long time. But again, I put a liability disclaimer on there. You have to remember that this stuff, this power can kill you. So you have to, shouldn't be scared of it. It's not very difficult wiring. You can learn a lot just by reading online. But you do have to take the caution and not think that it's just some walk in the park. You are working with a lot of current at some point, and you need to be conscious of that. So here's my BOM. I basically got an entire parts listing with manufacturers and parts numbers, quantities, pricing at the time to give you a general idea, although it's probably changed a lot since then. Prices seemingly always go up. So this will also come with it, and that's pretty much it. I think that if you have any questions, I can follow up with another video, but hopefully I've answered all of them and showed you in this technical overview of how this machine works and inside the panel, explain a little bit better. When I started, I didn't have anybody to really go side by side with me. I really relied on sites like MechMate Forum and CNC Zone and Joe's CNC to get most of my ideas, and consulted with other people that were just doing this as a hobby, and improved it in time. And hopefully you enjoyed this video, and if you did, hopefully you rate and subscribe. And if you're interested in the plans, feel free to send me a message. I'll probably end up posting a link soon to a website where you can get them. And that's that. Well, until the next video, I hope to see you guys again. I'll keep making videos and keep cutting. Thanks for watching.